The 8th of March, 1943. It is 11:34 in the morning at Royal Air Force Station Ludford Magna, a cold, windswept patch of Lincolnshire that is home to No. 101 Squadron, RAF Bomber Command. Inside the cavernous hangar, the air is thick with the smells of oil, hydraulic fluid, and the faint, sweet scent of high-octane aviation fuel. Leading aircraftman Arthur Finch, a 26-year-old aircraft finisher, a painter, in civilian terms, is folded into the cramped, metallic confines of the No. 2 port-inner fuel tank of an Avro Lancaster B Mark I, serial number R5868, call sign S for sugar. In one hand, he grips a battery-powered torch, its beam cutting a weak circle in the Stygian gloom. In the other, he holds a grease-stained notepad and a stub of a pencil, his voice a low, methodical murmur that is swallowed by the echoing aluminium tomb. Leak number 1, he dictated to himself, the words appearing as puffs of condensation in the cold air. Rivet seam between ribs 4 and 5. Dripping at a rate of, say 12 drops per minute. His torch beam moved, tracing the intricate skeleton of the wing's interior. Leak number 2. Solder joint on the internal baffle. Slower, this one. 8 drops per minute. The beam crept upwards, illuminating a structural stringer. Leak number 3. Reinforcing rivet on the main spar. A fast one, this. 15 drops a minute, at least. He shuffled his position, the rough metal scraping against his woolen overalls. His light found a grommet where an electrical cable passed through the tank's bulkhead. Leak number 4. Electrical loom penetration. Bloody hell. This one's a pisser. 20 drops per minute, easy. Finch tallied 11 distinct leaks in the No. 2 tank alone. The Lancaster, a magnificent beast of an aeroplane, had 6 main fuel tanks housed within its wings, with a total capacity of 2,154 imperial gallons. If each tank was weeping fuel at a similar average rate, this single aircraft was losing roughly 1.6 gallons of precious fuel every hour, just sitting on the ground. A typical bombing mission deep into the industrial heart of Germany, the dreaded Ruhr Valley, was an 8-hour ordeal. That meant this Lancaster would hemorrhage nearly 13 gallons of fuel into its own wing structure before a single Merlin engine was brought to full power. 13 gallons. It doesn't sound like an insurmountable amount, not when you have over 2,000 to begin with. But consider this, for the crews of Bomber Command, the margin between returning to the green fields of Lincolnshire or ditching in the unforgiving grey waters of the North Sea was often less than 20 gallons. A headwind on the return leg, a bit of extra time spent forming up, or a slightly longer route to avoid flak could burn through that reserve in minutes. But the problem wasn't merely the quantity of fuel lost, it was the insidious destination of that fuel. When the tanks leaked, the avgas didn't just vanish. It seeped into the structural compartments of the wings, pooling in the gaps between spars and ribs. It dripped onto electrical wiring, its volatile vapors filling the enclosed spaces, waiting for a single, stray spark. The Lancaster's fuel tanks were of a self-sealing design, a marvel of wartime engineering. They were constructed from layers of vulcanized rubber sandwiched between treated fabric. When a cannon shell or piece of shrapnel punctured the tank, the fuel would cause the rubber to swell, instantly plugging the hole. It was a system that worked brilliantly for combat damage. But it was utterly useless against the slow, persistent, structural weeping from rivet seams, solder joints, and cable penetrations. And these leaks, these tiny, insignificant drips, were killing aircrews just as surely as the Luftwaffe's night fighters. Between January and March of 1943, a grim period for Bomber Command, No. 5 Group lost 14 Lancasters to non-combat causes. Of those 14, a staggering 9 were attributed, directly or indirectly, to fuel leaks. There were fires, catastrophic explosions sparked by fuel vapor igniting on electrical systems. There were engines starving of fuel as tanks emptied far sooner than the gauges indicated, leading to fatal stalls on approach. There were crews forced to ditch or bail out over occupied Europe, their magnificent bombers running dry long before they could reach the English coast. Engineers from Avro and the Ministry of Aircraft Production were dispatched to investigate. Their findings were laid bare in a dry, technical report, map TR 443A, dated the 24th of February, 1943. Finch had managed to get his hands on a copy left behind in the engineering officer's briefing room. The language was cold, detached, almost clinical. The fuel tanks of the Lancaster BMKI are constructed via the assembly of alclad aluminium sections joined by aluminium alloy rivets and spot welding, it read. The nature of this riveted assembly method inevitably creates microscopic gaps between mating surfaces, attributable to manufacturing tolerances, structural stress deformation during flight, and differential thermal expansion. These leaks are inherent to the riveted construction design and cannot be eliminated by current sealing methods without a complete redesign of the wing and tank structure. The subtext was chillingly clear. The leaks are unavoidable. Live with them. Redesigning the aircraft would take 18 to 24 months. It would mean halting the production of Lancasters at a time when Bomber Command was losing them faster than they could be replaced. With the combined bomber offensive ramping up, stopping production was simply not an option. The official order from High Wycombe was to continue operations, to accept the leaks as an inherent risk, and to drill crews on emergency procedures for in-flight fuel fires. Leading aircraftman Arthur Finch, a painter from Portsmouth, read the report from the clever men with university degrees and came to a different conclusion. The engineers said the leaks couldn't be fixed with current sealing methods. Finch thought to himself, right then. Let's use a method that isn't current. If you want to know how one man's seemingly mad idea solved a problem that the brightest minds in British aviation had declared impossible, then please, press that like button, and subscribe if you haven't already. We'd be chuffed to have you with us. Arthur Finch was no engineer. He had no formal training beyond his apprenticeship. His official job was to spray the Lancasters with their standard night bomber camouflage, dark earth and dark green on the upper surfaces, a matte special night black underneath. But before the war, before the uniform and the flat, windswept airfield, Finch had spent 8 years as an industrial painter in the Portsmouth Naval Dockyard. There, amidst the colossal, steel flanks of destroyers and battleships, he had applied protective coatings to the inside of fuel bunkers. And in the dockyards, Finch had learned something that the engineers at Avro and the Ministry apparently did not. The fuel bunkers on His Majesty's ships had the exact same problem as the tanks on the Lancasters. They were vast, riveted constructions, and they leaked at the seams. The shipwrights had solved the problem by coating the inside of the bunkers with specialized sealants, creating a continuous, flexible membrane that covered every last seam, rivet, and weld. The most effective sealant Finch had ever used was a polysulfide adhesive that came from the Americans through the Lend-Lease program. It was called PR 1422, a thick, black goo developed by the Products Research Corporation for naval and aerospace applications. This PR 1422 had remarkable properties. It was impervious to aviation fuel. It was flexible, able to expand and contract with the metal of the tank through gut-wrenching temperature changes. It had a ferocious adhesion to aluminium, and it could cure in thick layers without cracking. The snag was, PR 1422 was designed to be applied to the external surfaces of tanks during their initial construction, not sloshed around inside a fully assembled, operational aircraft wing. Finch theorized that if he could devise a method to apply PR 1422 evenly to the interior of the Lancaster's existing fuel tanks, he could create that same continuous, sealed barrier, plugging every single leak simultaneously. The challenge was application. The Lancaster's tanks were confined spaces filled with a bewildering geometry of internal baffles, structural spars, cable runs, valves, and sensors. Trying to apply the sealant manually with a brush or roller would be an agonizingly slow and laborious task. It would take days for a single tank and would almost certainly result in an uneven, unreliable coating. Finch needed a method that was fast, efficient, and could coat every complex interior surface uniformly. And then, during a late-night brew in the smoky NAFI canteen, he had an idea that anyone else would have dismissed as completely barking mad. What if he could turn the thick, treacle-like sealant into a liquid paint? A paint thin enough to be sprayed, yet thick enough to seal the leaks once it cured. On the 10th of March, 1943, Finch requested a meeting with his engineering officer, Squadron Leader Evans, a weary but approachable man who had seen too many young crews fly out and not return. He asked for permission to experiment on a Lancaster that had been written off after suffering irreparable combat damage. It was our 5727, T for Tommy, which had limped back from a raid on Bremen with its rear fuselage shredded by flak. The structural damage was too extensive for economical repair. The aircraft was slated to be stripped for spares. Finch asked for permission to use its fuel tanks as a test bed. Squadron Leader Evans, intrigued by the sheer audacity of the Irk standing before him, authorized the test with one firm condition. Finch had 72 hours. If his method worked, he would receive the full backing of the squadron. If it failed, he was to return to his paint-spraying duties and never mention fuel tanks again. Finch got cracking immediately. Step 1. Develop the sealant formula. In its standard form, PR 1422 had the consistency of thick peanut butter. To spray it, Finch needed to dramatically reduce its viscosity without compromising its sealing properties. He began experimenting, mixing the PR 1422 with toluene, a powerful solvent that would thin the mixture but evaporate completely after application, leaving only the cured sealant behind. After several messy attempts, he determined the correct ratio through pure trial and error, 3 parts PR 1422 to 2 parts toluene. This created a mixture with the consistency of thick enamel paint, liquid enough to spray, yet viscous enough not to run excessively on vertical surfaces. But Finch added one more ingredient, a touch of genius born from his dockyard days that the Avro engineers had never considered: aluminium powder. The fine, metallic dust served two critical functions. First, it increased the thermal conductivity of the sealant, allowing it to cure more quickly and evenly when heat was applied. Second, and more importantly, it improved the adhesion to the aluminium of the tank, creating a powerful chemical and metallurgical bond between the sealant and the substrate. Finch's final, secret recipe was 3 parts PR 1422, 2 parts toluene, and half a part of 325 mesh-grade aluminium powder. Mixing this concoction required vigorous agitation for at least 15 minutes to disperse the aluminium powder evenly. Finch jury-rigged an electric paint mixer with a stainless steel paddle. The result was a silvery-gray substance with the consistency of thick paint and a sharp, penetrating smell of solvent. Step 2. Develop the application method. Finch needed to spray this mixture evenly across every internal surface. He sourced a conventional DeVilbiss pressure pot spray gun with a 2.0 mm nozzle, running it off the station's compressed air line. But spraying inside an enclosed fuel tank created an obvious and deadly problem. The toluene fumes would rapidly build up, creating a highly explosive atmosphere. A single spark from a tool, a static discharge from his overalls, and the entire wing would detonate. Finch solved this by rigging a forced air ventilation system. A powerful fan pushed fresh air into the tank through one opening at a rate of 200 cubic feet per minute, while an extractor fan simultaneously drew the solvent-laden vapors out through a second hatch. Step 3. Cure the sealant. PR 1422 normally took 48 hours to cure fully at ambient temperature. Finch didn't have 48 hours per tank. But he knew from the technical datasheet that the sealant could also be cured thermally. If exposed to a steady temperature of 65 degrees Celsius for 4 hours, it would cure completely. After spraying the sealant, Finch planned to place portable infrared electric heaters inside the tank, raising the internal temperature to precisely 65 degrees Celsius and holding it there for the required 4 hours. On the 12th of March, at 2:17 in the afternoon, Finch was ready for his first full-scale test. He selected the number 3 starboard tank of the crippled Lancaster. His own maintenance log showed that this tank had 17 documented leaks and was losing fuel at a rate of 3.1 gallons per hour when full. Kitted out in a heavy respirator mask, his spray gun in hand, and with the ventilation system roaring, Finch crawled into the tank. He worked methodically, his spray gun hissing as he coated every surface: the walls, the baffles, the rivet seams, the solder joints, the cable penetrations. The entire spraying process took 43 minutes and used just under 3 gallons of his special mixture. When he emerged, blinking in the hangar light, the tank's interior was completely coated in a uniform, 1.5 mm thick layer of glistening, silvery grey sealant. Finch installed the infrared heaters, sealed the tank's access panels, and began the thermal curing cycle. 4 hours and 12 minutes later, the sealant was rock hard but still flexible to the touch. He inspected his work with the torch. The sealant had formed a perfect, seamless barrier, bonded tightly to the aluminium, completely encasing every potential point of failure. Now came the ultimate test. Filling the tank with fuel and checking for drips. The next morning, the 13th of March, at 7:54 a.m., the number 3 tank was filled with 305 gallons of 100-octane aviation fuel and pressurized to 3 pounds per square inch, simulating flight conditions. With a knot in his stomach, Finch crawled into the wing's structural compartment beneath the tank, torch in hand, and began observing the areas where he had previously documented the worst leaks. The rivet seam between ribs 4 and 5, bone dry. The solder joint on the internal baffle, not a single drop. The reinforcing rivet on the main spar, completely sealed. The electrical loom penetration, utterly leak-free. Finch systematically inspected all 17 previously documented leak locations. 0 active leaks. 0 drips. 0 visible seepage. The tank was kept full and under pressure for a full 24 hours to confirm the seal was permanent, not just a temporary fix. After 24 hours, there were still no leaks. The Mad Irks method had worked. Finch reported his results to squadron leader Evans. The response was immediate and decisive. "You have authorization to modify every Lancaster in this squadron, Finch. How many men do you need, and how long will it take?" Finch did a quick calculation. With a trained team of 6 Irks, he could seal all 6 main tanks of a single Lancaster in approximately 18 hours of work, spread over 3 days to allow for curing times. No. 101 Squadron had 34 operational Lancasters on its strength at that moment. The total estimated time to seal the entire fleet, 6 weeks. Write sealant in the comments below if you are just discovering this incredible story. On the 15th of March, 1943, leading aircraftman Finch was given his team of 6 technicians and the green light to begin production. The process was standardized into a precise drill. 1. Completely drain and purge the fuel tank. 2. Clean the interior with solvent to remove all fuel residue and contaminants. 3. Dry the tank with hot compressed air. 4. Mix the sealant according to the exact formula. 5. Spray the sealant evenly over all internal surfaces. 6. Thermally cure the tank at 65 degrees Celsius for 4 hours. 7. Perform a final visual inspection, fill with fuel, and pressure check for any leaks. The average time per tank, including curing, was 8 hours. Total time per aircraft, 72 hours, spread over 3 days. With his team working simultaneously on different aircraft, Finch estimated he could process 2 Lancasters per week. By the 28th of April, 1943, all 34 of 101 Squadron's Lancasters had received the Finch treatment. The results were nothing short of miraculous. Before the modification, the squadron was averaging a fuel loss from leaks of roughly 2.1 gallons per hour per aircraft in flight. On an 8-hour mission, that equated to nearly 17 gallons of fuel wasted per bomber. After the modification, the fuel loss from leaks was reduced to less than 0.3 gallons per hour. Across an 8-hour mission, only 2.4 gallons were lost, an astonishing 87% reduction in fuel leakage. But the most significant impact was not on the fuel saved, it was on the elimination of explosive fuel vapors within the wing structures. Between May and August of 1943, No. 101 Squadron did not record a single non-combat fuel-related fire. Not one. Before the modification, the squadron had been averaging 1.3 such incidents per month. The station commanders of other squadrons in No. 5 Group began to notice. The operational readiness and, crucially, the morale of 101 Squadron had visibly improved. By June of 1943, The Finch method was officially adopted by RAF Bomber Command and authorized for implementation across the entire European theater. Between July 1943 and May 1945, an estimated 2,800 Lancasters were modified using variations of Finch's original process. The impact on operational losses was documented in a post-war technical report, AFT 5512, issued in December 1945. The implementation of the internal fuel tank sealant process, as developed by Lac. Finch, the report stated, resulted in a 76% reduction in non-combat fuel fires and a 43% reduction in forced landings due to premature fuel starvation. A conservative estimate of aircrew lives saved is between 2,800 and 3,400 during the period of implementation. 2,800 to 3,400 lives saved. That is approximately 400 to 480 complete 7-man Lancaster crews who returned home because Arthur Finch, a painter from Portsmouth, refused to accept that a problem was inherent to the design and impossible to solve. Yet Finch never received any public recognition during the war. The method was classified as sensitive technical information. Revealing that the backbone of Bomber Command had a significant fuel leak problem could have been disastrous for aircrew morale and would have provided valuable tactical intelligence to the enemy. Finch was quietly promoted from leading aircraftman to sergeant in July 1943, a standard increase in rank for a skilled technician that made no specific mention of his world-changing innovation. He received no medal for his technical ingenuity. His name never appeared in official communiques. The engineers at Avro eventually incorporated a modified version of his process into the later production runs of Lancasters, applying the sealant during the initial factory assembly. But the company never publicly acknowledged that a 26-year-old aircraft painter had single-handedly solved a problem their own qualified engineers had declared impossible. After the war, Arthur Finch returned to Portsmouth. He worked as a quality inspector in the naval dockyards for 32 years, retiring in 1977. He passed away peacefully in 2001, at the age of 84. His brief obituary in the Portsmouth Herald mentioned his service in the Royal Air Force during the Second World War, but it made no mention of the 2,800 Lancasters he sealed, or the thousands of lives he saved. But in the archives of the RAF Museum in Hendon, London, there is a beautifully restored Lancaster B Mark I, serial number R5868, the very same S for sugar that now stands as a monument to the crews who flew her. During her restoration in 1998, inspectors examined her original fuel tanks, which had been sealed using the Finch method back in 1944. A museum conservator documented the finding with a quiet, astonished note. The sealant applied using the Finch technique in 1944 shows zero degradation after more than 5 decades. The longevity of the material and the integrity of the application are extraordinary. This is a testament to both the quality of the work and the efficacy of the method developed. What do you think of this extraordinary story? Did you know the crucial role that such innovations, born not in a laboratory but in the cold hangars of a wartime airfield, played in the survival of Bomber Command's crews? Please, leave us your thoughts in the comments, and subscribe to our channel. Every week, we bring you verified, fascinating stories that changed the course of history. Activate the notification bell so you don't miss a single episode. Sometimes, the greatest solutions to complex engineering problems don't come from corporate laboratories or men with degrees. They come from the hands-on technicians, the Urks on the ground, who refuse to accept that something is impossible. That is the lesson Arthur Finch taught the world from a windswept base in Lincolnshire in 1943. It was a lesson that the aircraft manufacturers took years to acknowledge, but one that the 3,000 airmen who came home because of him never needed to be told. They flew in bombers sealed by a painter who decided that inherent to the design was not an